Welcome to NPTEL online course on fractals and multifractals. Basically, this course we planned as a two-part. One is the fractal part, and another one is the multifractal part. So, in the previous lectures, we have discussed the history behind the fractals. That means what motivated to generate the fractal, that we discussed in the first week of this course, which includes the construction of the Cantor set, Van Koch curve and the Sierpinski triangle, and thereby Professor Bernard B. Mandelbrot motivated to coin the term fractal based on their self-similar nature and their non-integer fractal dimension. So, the fractal can be defined in two ways. One is based on the self-similar nature. That means a fractal having a random self-similar nature is called the random fractal. A fractal having exact self-similar nature we calling as the deterministic fractal or regular fractal. In the random fractal, the self-similar nature is in the approximate way, whereas in the exact fractal, the self-similarity in the deterministic way, that is the exact self-similarity. So, based on this nature, the fractal is classified into random fractal and deterministic fractal. Then we discussed how to construct the fractal in a metric space. So, we discussed the systematical way, so in which the fractal is generated as a non-empty unique compact invariant subset of a complete metric space generated by the Banach fixed point theorem. Thereby we included partial similarity in the deterministic fractal. We discussed the condensation set, and thereby we introduced the partial similarity in the deterministic fractal. Then as application of fractal, we have discussed the fractal interpolation function. The fractal interpolation function for the given data set, we need to find the continuous function which passing through the given data set. The continuous function we obtained as a graph of a continuous function which is obtained as unique invariant non-empty subset of a complete metric space. The space is constructed by using the given set of data. Then that graph has a continuous function, associated continuous function. That continuous function passing through the given data, that continuous function we are calling as the fractal interpolation function. Later we discussed what are the different type of fractal interpolation function. Then what is the use of the scaling vector alpha I, and how the scaling vector change the pattern and behavior of the fractal interpolation function we discussed. So, in all the previous lectures we have discussed the how to generate the fractal by using the iterated function system in the complete metric space, in the deterministic fractal as well as in the fractal interpolation theory. Now, the question is, the fractal is random fractal and regular fractal. The regular fractal we constructed in the complete metric space by using the iterated function theory. Now, the random fractal is appearing in the nature. Now, the question is how to measure the size of the fractal. How big is the given fractal? How to classify the or measures the given fractal? We need some measure. For that, this second part we are going to discuss in detailed about how to classify or how to understand the fractal given in the metric space or in the naturally appearing fractals. For that, initially we are going to discuss fractal dimension. So, for that, the second half of this course will discuss on the multifractal measures. So, for understanding multifractal measure, one has to understand what is fractal dimension. So, fractal dimension says how big is my fractal or how the given fractal dense in the embedded space that we can measure by using the fractal dimension. Then we need to discuss the topological dimension and the Hausdorff dimension. Thereby we need to introduce what is the multifractal measures, and we need to discuss the multifractality nature of the fractal objects. So, in the second part of this course, we are going to mainly discuss on the 4 major part by giving some regular fractal and random fractals. So, let me start this second half by introducing what is fractal dimension. In the fractal dimension gives that if we have the complete metric space and we have one fractal, consider the deterministic fractal. How the fractal is dense in the given metric space or given complete metric space, now we are going to discuss in the systematical way. Now, let us consider the x comma d complete metric space. Then h of x denote a set of all non-empty compact subset of x. Take an element A belongs to h of x and let epsilon greater than 0, then this b of x of epsilon denote to the closed ball of radius epsilon at center a point x. That means, if we have the set A for a given epsilon greater than 0, then let b of x denotes the closed ball of radius epsilon at center x, a point taken from the set A. That means, b of x comma center x comma epsilon denotes set of all y such that y belongs to A such that the distance between x and y is less than or equal to epsilon. This we denoted as b of x comma epsilon, the closed ball of radius epsilon at center x in x. Then define an integer n of a comma epsilon, n of a comma epsilon as the least number of closed ball of radius epsilon needed to cover the set A. That is, n of A equal to smallest positive integer m such that A must be contained in union of this m number of closed balls. For some set of distinct point x n belongs x n is a subset of x. Listen, this is our complete metric space x. Now, A is a non-empty compact subset of this complete metric space. This is my A. Now, we are taking the center in x. We are taking center in x. X belongs to x. The b of a b ball, closed ball is defined, already we defined. Once again I am writing here, the b of x comma epsilon is taken as set of all y belongs to A or in the x such that distance between x and y must be less than or equal to epsilon. The previously I am writing here it as A, this need not be A, it can be x also. Now, the distance between x and y less than epsilon, this is the closed ball. Now, the n of A denote the least number of closed ball of radius epsilon needed to cover the set A. See, our x is the complete metric space and A is the compact subset of an non-empty compact subset of x. As per the definition of compact, if you are finding one open cover for this A, we can find the finite subcover for this A. This is the definition of compact set. Every open cover has a finite subcover. Here A is a compact set, therefore, we can find the open cover. Open cover is possible. For that open cover, we can find the finite subcover. But here we are taking B of x comma delta as the closed ball. Instead of open ball, we are taking the closed ball. Now we need to verify for such a whether the open ball is exist. One question. If the open cover is existing, then how to find the number of closed ball of radius epsilon needed to cover A? Then we need to take among, if A we have only one open cover or closed cover, whether we have more than one closed cover we need to check. Therefore, we have to take one minimum among all the covers. For that, for maybe this equation, this is already equal, this can be equivalently written as that n of A comma epsilon is defined as minimum among all the m such that A is embedded in union of B of x n comma epsilon for x n belongs to x. That means, we are taking one x here and find the closed ball of radius r. That means, it containing the boundary. This is my x 1 and you can take x 2 here and take radius and same radius and draw here, because A is a subset of x. If you are taking one element here and draw the same radius r, then radius r, we can find the open cover. So, because A is a compact set, we can find the open cover. For this open cover, we can find the finite subcover. If you are taking this x, all the x belongs to A and draw the closed ball or open ball with respect to the center x belongs to, instead of x, if you take A, then obviously it covers the set A. So, the open cover has a finite subcover, no doubt. Now, we need to check only the closed subcover. Now, if such a closed cover is exist, then we can find the minimum among all. That minimum we are denoting as the number of closed ball of radius epsilon is needed to cover the set A. Now, the existence of such a number is ensured by surrounding every point x belongs to A open ball of radius epsilon to be a cover of an A by open set. This is the definition of compact set. Then this cover possesses a finite subcover consisting of integer number m cap of open ball. Now, because every infinite cover has a finite subcover, this is the definition of compact set. Therefore, the infinite cover has a finite subcover. Say for example, that finite subcover has the m cap number of open balls. Now, by taking the closure of the open balls, one can obtain a open cover consisting of m cap number of closed balls. So, if you are taking the closure means the closure, if the ball of x comma epsilon is given, one can take the closure, that means the open ball means x comma epsilon, b of x comma epsilon is defined as set of all y belongs to A such that distance between y belongs to x such that distance between x and y is strictly less than epsilon. This is the open cover. So, as per the definition of the compact net, every infinite cover has a finite subcover. If you are taking the closure, then this strictly less than becomes the less than or equal to. That means, b of x comma epsilon union its limit points. limit point of B of x comma epsilon. So, it becomes the closed balls. This closed ball then obviously covers the set A. Therefore, for every infinite cover we can find the finite subcover of open balls. Then for taking the closure of open ball, one can get to the finite closed ball cover for the given compact set. Now, here the pictorial representation is given here. Let x comma d be a complete metric space and A is a non-empty compact subset of X. For epsilon greater than 0, B of x comma epsilon denote the closed ball of radius epsilon centered at x belongs to X. N of x is the smallest number of closed ball of epsilon needed to cover A, is equivalently written here. Now, the existence of such a ball, the collection of open ball, maybe do not confuse with this closed. I am not giving the two different notation. Maybe one can take this notation for the closed ball, this open is for the open ball. The collection of open ball is an open cover of A. Since A is compact, it has a finite subcover. By taking this closure of all these balls, one can get the closed balls which covers the A, and you can take the m bar. The n of A comma epsilon is less than or equal to m bar. Now, it is here, this is my x, this is my A. By taking the balls points in x, one can generate the open balls. Then this open balls has the finite subcover, that as per here the open ball has a finite subcover, it is given here. Now, cover by this, instead of this open ball, take the there are limit points, that means the closure of this open ball, it becomes the closed ball, it again covers the set A. So, here this purple line denote the open balls and red line denote the closed balls. Now, like that we can find the number of closed ball of radius epsilon needed to cover the set A, one can find. Now, let me explain by some example. Let us start A equal to 0 comma 1. Now, we need to find the open cover for this 0 comma 1. Then for that open cover we need to find the finite subcover and take the closure of that subcover, then find the number of closed balls are required to cover this A, we can calculate. Now, the closed interval 0 comma 1, consider the infinite open cover like this one, minus 1 comma n, 1 plus 1 by n. If you are taking the closed interval 0 comma 1, this is the open cover for closed interval 0 comma 1. If you are taking 1 as 1, one can get minus 1 by 2, and if you are taking n as 1, 1 plus 1 by 2, one can get 3 by 2. Then union, if you are taking n as 3 minus 1 by 3, n as 2 means one can get this one, n equal to 1, one can get minus 1 comma 1, 2, one can get union this number, and 2 means one can get this number, this interval, and 3 means minus 1 by 3, 1 plus 1 by 3, so 5 by 3. Now, one can observe that if you are taking any element in x belongs to closed interval 0 comma 1, obviously x belongs to this cover, that means it goes on like this one and it goes on infinite covers. So, it belongs to this cover. So, then this set covers the set closed interval 0 comma 1, this is minus 1 by 2, minus 1 to 2, obviously this single set alone covers the closed interval 0 comma 1. Now, 0 comma 1 is compact set, there exists a finite subcover. For example, if you are taking this set alone minus 1 by 2, minus 1 comma 2, this minus 1 comma 2 covers the 0 comma 1 entirely. So, for this infinite cover, for this infinite cover. The trivial finite open cover is, you can take U1. U1 itself covers the closed interval 0 comma 1. Then the closure of this one, for finding the closure of this one, U1 comma the limit point of U1. The limit point of U1 is minus 1 and 2. Minus 1 and 2. Therefore, this set minus 1 closed interval minus 1 comma 2 will forms the finite closed subcover of A. So, we started with the infinite cover, infinite open cover, because here the open interval is open set. Here for this infinite open set, we are finding the finite open set, the trivial cover, simply we are taking minus 1 comma 2. Now, you can take the closure of this U1, that is the set U1 union the limit point of U1, one can get the closed ball minus 1 comma 2. If minus 1 comma 2 covers the set A, then obviously minus 1 comma 2 the closed ball also covers the set A, because this 0 comma 1 contained in the U1 bar. So, one can find the closure of the open cover, finite open cover, then get the closed subcover of the given set. Now, this is the trivial cover. Now, one can consider the infinite open cover of the closed interval 0 comma 1 as this open cover. So, previously we considered minus 1 by n comma 1 plus 1 by n. If you are replacing n as 1, one can get minus 1 comma 2. Exactly when you are taking n as 1, it is entirely cover the 1. Whereas here if you are taking U1, the U1 here, one can get 1. So, one can get 0 comma this 1 you can get 2, 0 comma 2. Then if you are taking n as 2, 2 minus 1, 1 over 2 comma here take 3 by 2. Initially 2, then reduced to 3 by 2, then this one is increased to 1 by 2. So, this open cover basically around the point 1, This is a more localized open cover compared with the previous one, where each interval covers a neighborhood around the point approaching the 1. Here you can see this is decreasing, this end is increasing, this end is increasing, both are convergent to 1. So, each subinterval covers a neighborhood around the point approaching 1. We can select the finite subcover U1, U2, U3, U4. U1, U2, U3, U4, then it covers the closed interval 0 comma 1. Now, take the closure of this all the covers U1, U2, U3, U4, then one can get the closed subcover of 0 comma 1. Now, this closed subcover, that means that this one 0 comma 1 contained in the closed balls, all the closed balls. So, likewise if any set is given, we can find the closed subcover. In particular, that closed subcover is finite subcover. So, hence a compactness guarantees that existence of a finite subcover even in non-trivial covers. Here it is a trivial cover, here we are finding the non-trivial covers. So, we can find the finite closed subcover of a given compact set. So, if you are finding the finite subcovers, then we can find number of closed ball is required to cover the A, we can count it. Therefore, then term n, this term n is n comma epsilon is always exist for a given compact set. Now, for defining the fractal dimension, let C denote the set of covers of A by at most m bar closed balls of radius epsilon. then C containing at least one element. So, what is C? C is denote the set of covers of A by at most m bar closed balls of radius epsilon. That means, if you are taking set of covers of U, if you are taking A is contained in, I am denoting as cover of A as the script I, this Ci variance over I. C is set of all this script C such that A contained in this open cover, even each element C contains the I equal to 1 to m bar number of sets. Otherwise, if A is compact set, we can find the infinite open cover. For that infinite open cover, we can always find an finite open cover. Take the closure of the finite open cover, one can get the closed covers. So, the m bar is exist. Now, C denote the set of all covers of A by at most m. So, if you are taking C1, C2, C3, that C m cap number of balls, closed balls, if you are taking the union, it covers the A. This each collection I can call it as C. Then C containing at least one element, because there exists a trivial open cover. If you are taking the compact set, that compact set you can take the end. If you are taking any compact set A contained in A. So, at one existing non-trivial is very trivial. Now, F containing at least one element. Now, I am defining the function F from C to the finite set 1 to m cap be defined by, if you are taking one open cover in C, that maps the number of ball in the cover C belongs to C. The number of balls in the cover C belongs to C. If this C forms the cover of A, then the C has maximum m cap number of closed balls. Now, this F of C denote the number of balls in the cover. Suppose it is m cap, so there are infinite number of covers in which each cover has maximum m cap number of closed balls. So, then this F of C over C belongs to is a finite set of positive integer. This is a finite set of positive integer, therefore, it has the minimum elements. Any finite set of positive integer has a minimum element, that least element we are denoting as n of a comma epsilon. So, n of a comma epsilon is the minimum number of closed balls is required to cover the set A. So, this number is always exist for any compact set A. Now, the intuitive idea behind the fractal dimension is that a set A has a fractal dimension if this number of the closed ball is required to cover the box A is directional proportional to C times epsilon power minus d for some positive constant C. Here epsilon is the size of the closed ball, that means the radius of the closed ball. That means, if you are taking x comma epsilon, x is the center, the epsilon is the radius. The epsilon denote the radius of the closed balls which is required to cover the set A. Here we use the notation this tilde as follows: let f of x and g of x be real valued function of the positive real variable epsilon, the meaning of this f epsilon tilde g epsilon means that whenever the limit epsilon tends to 0, the natural logarithm of f of epsilon over natural logarithm of g of epsilon equal to 1. Whenever this approaches to 0, the ratio between logarithm of these two number equals 1. Now we will define the what is fractal dimension. Now this one can obtain as n of a of epsilon c of epsilon power minus d. Take the natural logarithm on both sides, n of a epsilon tilde natural logarithm of c of epsilon power tilde, which we already given as 1. Therefore, this can be splitted as, that means natural logarithm of n of a comma epsilon over natural logarithm of c comma epsilon d equals 1, which implies natural logarithm of n of a comma epsilon which is equal to n of natural logarithm of c and natural logarithm of, if we are applying the logarithm property, one can add epsilon power minus d. If limit epsilon tends to 0, if yes, this can be minus d, then our intention is we need to find the d value. If here comes the d is front side, so minus d can be written as this is in the product, so this is in the plus, so minus ln epsilon equal to ln n of a comma epsilon minus ln c. Now from here one can get, I can write here, so if you are finding the d equals say natural logarithm of n of a comma epsilon over ln of epsilon minus then minus ln c over ln of epsilon, this is we can make it plus. Now whenever this epsilon tends to 0, one can obtain by applying this property, one can apply the d. Our intention is we need to fractal dimension d, so one can get d as like this one. Now d is equal to approximately equal to this one. Whenever you are taking epsilon tends to 0, one can get the value d. Now here this c is the constant term, this c is a constant term. Why I am writing the plus? No, it is minus only here. It is taking the ln c, while here continuing it is a minus. Yes, fine. Now if this ln c is a constant number, whenever this term epsilon tends to 0, limit epsilon tends to 0, this becomes 0, because 1 by epsilon increasing, the 1 by epsilon is increasing. So this one will goes to 0, so one can get this term as 0. Finally one can get the formula, this one d equals limit epsilon tend to 0, one can take ln of n of a comma epsilon over ln of epsilon. We can write it minus also, that this is we can write minus, then 1 by epsilon it will come. Okay. So now the d is obtained by this one. Then now we are ready to give the definition of fractal dimension. Let A belongs to h of x, where h comma d is a metric space, where h of x is the collection of all non-empty compact subsets of this x comma d, and A is any member of h of x. For each epsilon greater than 0, let n of a comma epsilon denote the smallest number of closed ball of radius epsilon needed to cover the set A. we already discussed the existence of n of a, that means n of a comma epsilon for every compact set. If any compact set we can find, and if the D equal to limit epsilon tends to 0, the natural logarithm of that number of boxes required to cover the set A over the closed ball of radius epsilon, that epsilon we are writing as here, the closed ball radius is given here, then ln of 1 by epsilon. If this limit exists, then D is called the fractal dimension of the set A. We will also use the notation D equal to D of A to say a fractal dimension of a set A. Now, one can note that the fractal dimension we can find for any non-empty compact set, not only fractal object. This dimension, this is we can call it the box counting method to find the fractal dimension. This fractal dimension we can find for any set, not only fractal set. If such a limit exists for any non-empty compact set A, then we can call it as such a number D is a fractal dimension of a given set A. Now, one can understand what is the this D means, what is the meaning of this D. You can observe that we are taking the set A and finding the number of closed covers. For the set A, we may get finite, A is compact set, it has a open cover, infinite number of open cover, this infinite number of open cover has a finite subcover, one thing. By taking the closure of the finite open cover, we can get the finite closed cover, but the finite closed cover is not a unique, it may be many covers, open covers. So, for this A can be covered by the many closed finite covers, but we are taking minimum among all the closed covers, that is n of a comma epsilon. N of a comma epsilon is minimum among all the closed cover. Now, we are fixing the given epsilon greater than 0, we are finding the closed cover. So, if varying the epsilon, one can get the finer approximation of A, because the closed cover of radius epsilon, whenever you are varying the epsilon, your closed cover will vary. So, whenever this epsilon is lesser and lesser, then n of the number of balls required to cover A will increase. So, one can get the finer approximation when you take this epsilon to 0, one can get the finer approximation. So, that we are taking limit epsilon tends to 0, we are taking the ratio between limit between natural logarithm of closed number of ball required to cover the set A, we are taking the minimum and over the size of the closed balls. So, it says how big is this set A. So, by using the D, one can say how this set VR is a subset of X, complete metric space. By finding the D, one can say how much this set A is dense in the set X. That means how the set A is distributed in the set X by using the covering of the closed balls, covering of the closed balls. So, this dimension D we are calling as the, this exponent D we are calling as the fractal dimensions. So, in the next lecture we can find how to find the fractal dimension of any non-empty compact sets. So, one can refer these books for the more details. Thank you.